In the mathematical field of differential geometry, a metric tensor is a type of function which takes as input a pair of tangent vectors v and w at a point of a surface and produces a real number scalar g, v, w, in a way that generalizes many of the familiar properties of the dot product of vectors in Euclidean space. In the same way as a dot product, metric tensors are used to define the length of an angle between tangent vectors. A metric tensor is called positive definite if it assigns a positive value to every non-zero vector. A manifold equipped with a positive definite metric tensor is known as a Riemannian manifold. Through integration, the metric tensor allows one to define and compute the length of curves on the manifold. On a Riemannian manifold, the curve connecting two points that has the smallest length is called a geodesic, and its length is the distance that a passenger in the manifold needs to traverse to go from one point to the other. Equipped with this notion of length, a Riemannian manifold is a metric space, meaning that it has a distance function d, p, q, whose value at a pair of points p and q is the distance from p to q. Conversely, the metric tensor itself is the derivative of the distance function. Thus the metric tensor gives the infinitesimal distance on the manifold. While the notion of a metric tensor was known in some sense to mathematicians such as Carl Gauss from the early 19th century, it was not until the early 20th century that its properties as a tensor were understood by, in particular, Gregorio Ricci Curbastro and Tullio Levi Civita, who first codified the notion of a tensor. The metric tensor is an example of a tensor field. The components of a metric tensor in a coordinate basis take on the form of a symmetric matrix whose entries transform covariantly under changes to the coordinate system. Thus a metric tensor is a covariant symmetric tensor. From the coordinate-independent point of view, a metric tensor is defined to be a non-degenerate symmetric bilinear form on each tangent space that varies smoothly from point to point. Introduction. Carl Friedrich Gauss in his 1827 Disquisitions generales circa superficies curvae considered a surface parametrically, with the Cartesian coordinates x, y, and z of points on the surface depending on two auxiliary variables u and v. Thus a parametric surface is a vector-valued function. Depending on an ordered pair of real variables, and defined in an open set D in the U-V plane. One of the chief aims of Gauss investigations was to deduce those features of the surface which could be described by a function which would remain unchanged if the surface underwent a transformation in space, or a change in the particular parametric form of the same geometrical surface. One natural such invariant quantity is the length of a curve drawn along the surface. Another is the angle between a pair of curves drawn along the surface and meeting at a common point. A third such quantity is the area of a piece of the surface. The study of these invariants of a surface led Gauss to introduce the predecessor of the modern notion of the metric tensor. Arc length equals, if the variables u and v are taken to depend on a third variable, t, taking values in an interval, a, b, then will trace out a parametric curve in parametric surface M. The arc length of that curve is given by the integral, where represents the Euclidean norm. Here the chain rule has been applied, and the subscripts denote partial derivatives. The integrand is the restriction to the curve of the square root of the differential, where the quantity ds in is called the line element, while ds2 is called the first fundamental form of M. Intuitively, it represents the principal part of the square of the displacement undergone by when u is increased by d units, and v is increased by dv units. Using matrix notation, the first fundamental form becomes coordinate transformations equals, suppose now that a different parameterization is selected, by allowing u and v to depend on another pair of variables where euro squared and var euro squared. Then the analog of for the new variables is. The chain rule relates a euro squared, var euro squared, and gar euro squared to e, f, and g via the matrix equation, where the superscript T denotes the matrix transpose. The matrix with the coefficients E, F, and G arranged in this way therefore transforms by the Jacobian matrix of the coordinate change. A matrix which transforms in this way is one kind of what is called a tensor. The matrix with the transformation law is known as the metric tensor of the surface. equals invariance of arc length under coordinate transformations equals. Ricci Curbastro and Levi Civet have first observed the significance of a system of coefficients E, F, and G, that transformed in this way on passing from one system of coordinates to another. The upshot is that the first fundamental form is invariant under changes in the coordinate system, and that this follows exclusively from the transformation properties of E, F, and G, indeed, by the chain rule. So that equals length and angle equals. Another interpretation of the metric tensor, also considered by Gauss, is that it provides a way in which to compute the length of tangent vectors to the surface, as well as the angle between two tangent vectors. In contemporary terms, the metric tensor allows one to compute the dot product of tangent vectors in a manner independent of the parametric description of the surface. Any tangent vector at a point of the parametric surface M can be written in the form for suitable real numbers p1 and p2. If two tangent vectors are given, then using the bilinearity of the dot product. This is plainly a function of the four variables a1, b1, a2, and b2. It is more profitably viewed, however, as a function that takes a pair of arguments a equals, a1 a2, and b equals, b1 b2, which are vectors in the U-plane. That is, put. This is a symmetric function in A and B, meaning that it is also bilinear, meaning that it is linear in each variable A and B separately. That is, for any vectors A, or euro squared, B, and bar euro squared in the U-plane, and any real numbers I1/4 and I. In particular, the length of a tangent vector A is given by, and the angle I between two vectors A and B is calculated by equals area equals. The surface area is another numerical quantity which should depend only on the surface itself, and not on how it is parameterized. If the surface M is parameterized by the function over the domain D in the U-plane, then the surface area of M is given by the integral, where A denotes the cross product, and the absolute value denotes the length of a vector in Euclidean space. By Lagrange's identity for the cross product, the integral can be written where det is the determinant. Definition: let M be a smooth manifold of dimension n. For instance, a surface or hypersurface in the Cartesian space Rn+1. At each point Pm there is a vector space Tpm, called the tangent space, consisting of all tangent vectors to the manifold at the point P. A metric at P is a function Gp, xp, yp, which takes as inputs a pair of tangent vectors xp and yp at P, and produces as an output a real number, so that the following conditions are satisfied: Gp is bilinear. A function of two vector arguments is bilinear if it is linear separately in each argument. Thus if up, Vp, up are three tangent vectors at P and A and B are real numbers, then Gp is symmetric. A function of two vector arguments is symmetric provided that for all vectors xp and yp, Gp is non-degenerate. A bilinear function is non-degenerate provided that, for every tangent vector xp apermel 0, the function obtained by holding xp constant and allowing yp to vary is not identically 0. That is, for every xp apermel 0 there exists a yp such that gp, xp, yp, apermel 0. A metric tensor G on M assigns to each point P of M a metric Gp in the tangent space at P in a way that varies smoothly with P. More precisely, given any open subset U of manifold M and any vector fields X and Y on U, the real function is a smooth function of P. Components of the metric. The components of the metric in any basis of vector fields, or frame, F equals are given by the n2 functions Gij, F, form the entries of a now, n-symmetric matrix, G, F. If are two vectors at P or U, then the value of the metric applied to V and W is determined by the coefficients by bilinearity. Denoting the matrix by G, F, and arranging the components of the vectors V and W into column vectors V, F, and W, F. Where V, F, T and W, F, T denote the transpose of the vectors V, F, and W, F, respectively. Under a change of basis of the form For some invertible NA, N matrix A equals, the matrix of components of the metric changes by A as well. That is, or, in terms of the entries of this matrix. For this reason, the system of quantities Gij, F, is said to transform covariantly with respect to changes in the frame F. Equals metric in coordinates equals, a system of n real-valued functions, giving a local coordinate system on an open set U and M, determines a basis of vector fields on U. The metric G has components relative to this frame given by relative to a new system of local coordinates, say. The metric tensor will determine a different matrix of coefficients. This new system of functions is related to the original Gij, F, by means of the chain rule. So that, or, in terms of the matrices G, F, equals and G, phi euro squared equals, where dy denotes the Jacobian matrix of the coordinate change, equals signature of a metric equals. Associated to any metric tensor is the quadratic form defined in each tangent space by. If Qm is positive for all non-zero xm, then the metric is positive definite at m. If the metric is positive definite at every m, then G is called a Riemannian metric. More generally, if the quadratic forms Qm have constant signature independent of m, then the signature of G is this signature, and G is called a pseudo-Riemannian metric. If m is connected, then the signature of Qm does not depend on m. By Sylvester's law of inertia, a basis of tangent vectors xi can be chosen locally so that the quadratic form diagonalizes in the following manner. For some p between 1 and n, any two such expressions of Q will have the same number p of positive signs. The signature of G is the pair of integers, signifying that there are p positive signs and n p negative signs in any such expression. Equivalently, the metric has signature if the matrix Gij of the metric has p positive and n p negative eigenvalues. Certain metric signatures which arise frequently in applications are, if G has signature, then G is a Riemannian metric, and M is called a Riemannian manifold. Otherwise, G is a pseudo-Riemannian metric, and M is called a pseudo-Riemannian manifold. If M is four-dimensional with signature or, then the metric is called Lorentzian. More generally, a metric tensor in dimension n other than 4 of signature or is sometimes also called Lorentzian. If M is 2n-dimensional and G has signature, then the metric is called ultra-hyperbolic. Equals inverse metric equals, let F equals be a basis of vector fields, and as above let G, F, be the matrix of coefficients. One can consider the inverse matrix G, F, A1, which is identified with the inverse metric. The inverse metric satisfies a transformation law when the frame F is changed by a matrix A via. The inverse metric transforms contravariantly, or with respect to the inverse of the change of basis matrix A. Whereas the metric itself provides a way to measure the length of vector fields, the inverse metric supplies a means of measuring the length of covector fields. That is, fields of linear functionals. To see this, suppose that I plus or minus is a covector field. To wit, for each point P, I plus or minus determines a function I plus or minus P defined on tangent vectors at P so that the following linearity condition holds for all tangent vectors x P and IP, and all real numbers A and B. As P varies, I plus or minus is assumed to be a smooth function in the sense that is a smooth function of P for any smooth vector field X. Any covector field I plus or minus has components in the basis of vector fields F. These are determined by. Denote the row vector of these components by. Under a change of F by a matrix A, I plus or minus, F, changes by the rule. That is, the row vector of components I plus or minus, F, transforms as a covariant vector. For a pair I plus or minus and I squared of covector fields, define the inverse metric applied to these two covectors by. The resulting definition, although it involves the choice of basis F, does not actually depend on F in an essential way. Indeed, changing basis to Fa gives so that the right-hand side of equation is unaffected by changing the basis F to any other basis Fa whatsoever. Consequently, The equation may be assigned a meaning independently of the choice of basis. The entries of the matrix G, F, are denoted by Gij, where the indices I and j have been raised to indicate the transformation law. Equals raising and lowering indices equals. In a basis of vector fields F equals, any smooth tangent vector field X can be written in the form. For some uniquely determined smooth functions V1, Vn. Upon changing the basis F by a non-singular matrix A, the coefficients phi change in such a way that equation remains true. That is, consequently, V, Fa equals or 1V, F. In other words, the components of a vector transform contravariantly under a change of basis by the non-singular matrix A. The contravariance of the components of V, F, is notationally designated by placing the indices of I, F, in the upper position. A frame also allows covectors to be expressed in terms of their components. For the basis of vector fields F equals, define the dual basis to be the linear functional such that is, II, F, xj, equals Ig, the Kronecker delta. Let. Under a change of basis Fa for a non-singular matrix A, I, F, transforms via. Any linear functional I plus or minus on tangent vectors can be expanded in terms of the dual basis I, where A, F, denotes the row vector, A1, F, an, F. The components I transform when the basis F is replaced by Fa in such a way that equation continues to hold. That is, whence, because I, Fa equals or 1I, F, it follows that a, Fa equals A, F, A. That is, the components are transformed covariantly. The covariance of the components of A, F, is notationally designated by placing the indices of I, F, in the lower position. Now, the metric tensor gives a means to identify vectors and covectors as follows. Holding xp fixed, the function of tangent vector at defines a linear functional on the tangent space at P. This operation takes a vector xp at a point P and produces a covector gp, xp, A. In a basis of vector fields F, if a vector field X has components V, F, then the components of the covector field G, X, and the dual basis are given by the entries of the row vector. Under a change of basis Fa, the right-hand side of this equation transforms via. So that a, Fa equals A, F, A transforms covariantly. The operation of associating to the components of a vector field V, F, equals, V1, F, V2, F, Vn, F, A euro T. The components of the covector field A, F, equals, A1, F, A2, F, an, F, A euro, where is called lowering the index. To raise the index, one applies the same construction but with the inverse metric instead of a metric. If A, F, equals, A1, F, A2, F, an, F, A euro are the components of a covector and the dual basis I, F, then the column vector has components which transform contravariantly. Consequently, the quantity X equals Fe, F, does not depend on the choice of basis F in an essential way, and thus defines a vector field on M. The operation associating to the components of a covector A, F, the components of a vector V, F, given is called raising the index. In components, is equals induced metric equals, let U be an open set in Rn, and let I be a continuously differentiable function from U into the Euclidean space Rm, where M, N. The mapping I is called an immersion if its differential is injective at every point of view. The image of I is called an immersed submanifold. Suppose that I is an immersion onto the submanifold M*M. The usual Euclidean dot product in Rm is a metric which, when restricted to vectors tangent to M, gives a means for taking the dot product of these tangent vectors. This is called the induced metric. Suppose that V is a tangent vector at a point of view, say, where I are the standard coordinate vectors in Rn. When I is applied to U, the vector V goes over to the vector tangent to M given by This is called the push-forward of V along I. Given two such vectors, V and W, the induced metric is defined by. It follows from a straightforward calculation that the matrix of the induced metric in the basis of coordinate vector fields E is given by, where D is the Jacobian matrix. Intrinsic definitions of a metric. The notion of a metric can be defined intrinsically using the language of fiber bundles and vector bundles. In these terms, a metric tensor is a function from the fiber product of the tangent bundle of M with itself to A such that the restriction of G to each fiber is a non-degenerate bilinear mapping. The mapping is required to be continuous, and often continuously differentiable, smooth, or real analytic, depending on the case of interest, and whether M can support such a structure. Equals metric as a section of a bundle equals, by the universal property of the tensor product, any bilinear mapping gives rise naturally to a section gash, of the dual of the tensor product bundle of Tm with itself. The section gash is defined on simple elements of Tmash, Tm by, and is defined on arbitrary elements of Tmash, Tm by extending linearly to linear combinations of simple elements. The original bilinear form G is symmetric if and only if. Where is the braiding map? Since M is finite-dimensional, there is a natural isomorphism. So that gash is regarded also as a section of the bundle Tmash, Tm of the cotangent bundle Tm with itself. Since G is symmetric as a bilinear mapping, it follows that gash is a symmetric tensor. Equals metric in a vector bundle equals, more generally, one may speak of a metric in a vector bundle. If E is a vector bundle over a manifold M, then a metric is a mapping from the fiber product of E to A which is bilinear in each fiber. Using duality as above, a metric is often identified with a section of the tensor product bundle. Equals tangent cotangent isomorphism equals. The metric tensor gives a natural isomorphism from the tangent bundle to the cotangent bundle, sometimes called the musical isomorphism. This isomorphism is obtained by setting, for each tangent vector xp a TPM. The linear functional on TPM which sends a tangent vector ip at p to gp, xp, ip. That is, in terms of the pairing, a between TPM and its dual space TPM. For all tangent vectors xp and ip. The mapping Sg is a linear transformation from TPM to TPM. It follows from the definition of non-degeneracy that the kernel of Sg is reduced to zero, and so by the rank nullity theorem, Sg is a linear isomorphism. Furthermore, Sg is a symmetric linear transformation in the sense that for all tangent vectors xp and ip. Conversely, any linear isomorphism S, TPM a TPM defines a non-degenerate bilinear form on TPM by means of. This bilinear form is symmetric if and only if S is symmetric. There is thus a natural one-to-one correspondence between symmetric bilinear forms on TPM and symmetric linear isomorphisms of TPM to the dual TPM. As P varies over M, Sg defines a section of the bundle Hom, Tm, of vector bundle isomorphisms of the tangent bundle to the cotangent bundle. This section has the same smoothness as G, it is continuous, differentiable, smooth, or real analytic according as G. The mapping Sg, which associates to every vector field on M a covector field on M gives an abstract formulation of lowering the index on a vector field. The inverse of Sg is a mapping Tm a Tm which, analogously, gives an abstract formulation of raising the index on a covector field. The inverse scar1 defines a linear mapping, which is non-singular and symmetric in the sense that for all covectors I plus or minus, I squared. Such a non-singular symmetric mapping gives rise to a map, or by the double dual isomorphism to a section of the tensor product. Arc length and the line element, suppose that G is a Riemannian metric on M. In a local coordinate system I equals 1, 2, n, the metric tensor appears as a matrix, denoted here by G, whose entries are the components Gij of the metric tensor relative to the coordinate vector fields. Let be a piecewise differentiable parametric curve in M, for A permale currency T A permale currency B. the arc length of the curve is defined by. In connection with this geometrical application, the quadratic differential form is called the first fundamental form associated to the metric, while ds is the line element. When ds2 is pulled back to the image of a curve in M, it represents the square of the differential with respect to arc length. For a pseudo-Riemannian metric, the length formula above is not always defined, because the term under the square root may become negative. We generally only define the length of a curve when the quantity under the square root is always of one sign or the other. In this case, define. Note that, while these formulas use coordinate expressions, they are in fact independent of the coordinates chosen. They depend only on the metric, and the curve along which the formula is integrated. Equals the energy, variational principles and geodesics equals, given a segment of a curve, another frequently defined quantity is the energy of the curve. This usage comes from physics, specifically, classical mechanics, where the integral E can be seen to directly correspond to the kinetic energy of a point particle moving on the surface of a manifold. Thus, for example, in Jacobi's formulation of Morpurtui principle, the metric tensor can be seen to correspond to the mass tensor of a moving particle. In many cases, whenever a calculation calls for the length to be used, a similar calculation using the energy may be done as well. This often leads to simpler formulas by avoiding the need for the square root. Thus, for example, the geodesic equations may be obtained by applying variational principles to either the length or the energy. In the latter case, the geodesic equations are seen to arise from the principle of least action. They describe the motion of a free particle that is confined to move on the manifold, but otherwise moves freely, with constant momentum, within the manifold. Canonical measure and volume form. In analogy with the case of surfaces, a metric tensor on an n-dimensional paracompact manifold M gives rise to a natural way to measure the n-dimensional volume of subsets of the manifold. The resulting natural positive Borel measure allows one to develop a theory of integrating functions on the manifold by means of the associated Lebesgue integral. A measure can be defined, by the Rice representation theorem, by giving a positive linear functional I on the space CO, M, of compactly supported continuous functions on M. More precisely, if M is a manifold with a Riemannian metric tensor G, then there is a unique positive Borel measure I1/4 G such that for any coordinate chart, for all E supported in U. Here det G is the determinant of the matrix formed by the components of the metric tensor in the coordinate chart. That I is well defined on functions supported in coordinate neighborhoods is justified by Jacobian change of variables. It extends to a unique positive linear functional on CO, M, by means of a partition of unity. If M is in addition oriented, then it is possible to define a natural volume form from the metric tensor. In a positively oriented coordinate system, the volume form is represented as where the dxi are the coordinate differentials and the wedges section denotes the exterior product in the algebra of differential forms. The volume form also gives a way to integrate functions on the manifold, and this geometric integral agrees with the integral obtained by the canonical Borel measure. Examples equals the Euclidean metric equals. The most familiar example is that of elementary Euclidean geometry, the two-dimensional Euclidean metric tensor. In the usual coordinates, we can write the length of a curve reduces to the formula. The Euclidean metric in some other common coordinate systems can be written as follows. Polar coordinates. So, by trigonometric identities. In general, in a Cartesian coordinate system xi on a Euclidean space, the partial derivatives are orthonormal with respect to the Euclidean metric. Thus the metric tensor is the Kronecker delta IH in this coordinate system. The metric tensor with respect to arbitrary coordinates is given by the round metric on a sphere. The unit sphere NA3 comes equipped with a natural metric induced from the ambient Euclidean metric. In standard spherical coordinates, with the colatitude, the angle measured from the z-axis, and the angle from the x-axis and the xy plane, the metric takes the form. This is usually written in the form equals Lorentzian metrics from relativity equals in flat Minkowski space, with coordinates the metric is. For a curve with the for example constant time coordinate, the length formula with this metric reduces to the usual length formula. For a time-like curve, the length formula gives the proper time along the curve. In this case, the space-time interval is written as. The Schwarzschild metric describes the space-time around a spherically symmetric body, such as a planet, or a black hole. With coordinates, we can write the metric as, where g is the gravitational constant and m represents the total mass-energy content of the central object. See also, Basic Introduction to the Mathematics of Curved Space-Time, Clifford Algebra, Finzler Manifold, List of Coordinate Charts, Ricci Calculus, Tissot's Indicatrix, a technique to visualize the metric tensor. Notes. References, Dodson, C.T.J. Poston, T., Tensor Geometry, Graduate Texts in Mathematics 130, Berlin, New York, Springer Verlag, ISBN 978-3-540-52018-4, Mr. 1223091, Galot, Sylvester. Hullin, Dominique. Lafontaine, Jack, Riemannian Geometry, Berlin, New York, Springer Verlag, ISBN 978-3-540-20493-0. Gauss, Carl Friedrich, General Investigations of Curved Surfaces, New York, Raven Press, translated by A. M. Hilterbeidl and J. C. Moorhead. Disquisitions Generals circa superficies curvas, Commentations Societatis Regiae Scientiarum Gottingensis Recentiores vol. 6, pages 99-146. Hawking, S. W. Ellis, G.F.R., The Large-Scale Structure of Space-Time, Cambridge University Press. K. David, Schaum's Outline of Theory and Problems of Tensor Calculus, McGraw-Hill, ISBN 978-0-07-033484-7. Klein, Morris, Mathematical Thought from Ancient to Modern Times, Volume 3, Oxford University Press. Lee, John, Riemannian Manifolds, Springer Verlag, ISBN 978-0-387-98322-6. Micah, Peter W., Topics in Differential Geometry, Graduate Studies in Mathematics, Volume 93, Providence, American Mathematical Society. Missner, Charles W. Thorne, Kip S. Wheeler, John A., Gravitation, W. H. Freeman, ISBN 0-7167-0344-0, Ricci Cabastro, Gregorio. Levi Civita, Tullio, Mar Copyright Thodes de Calcul for Copyright Rential Epsilon A Les Applications, Mathematicianalen 54, 125 €201, doi, 10.1007/BF014542001, ISSN 1432-1807, Sternberg, S., Lectures on Differential Geometry, New York, Chelsea Publishing Company, ISBN 0-8218-1385-4, Vaughan, Michael T., Introduction to Mathematical Physics, Weinheim, Wiley VCH Verlag GmbH and Company, ISBN 978-3-527-40627-2, Mr. 2324500 Wells, Raymond, Differential Analysis on Complex Manifolds, Berlin, New York, Springer Verlag.